Okay, so I want to talk a little bit about information today. Um, Information is closely related to the state of the system. It's essentially the knowledge we have about what state a physical system is actually in. And generally, we gain this through making observations. Let's do the coin flip example since we use that in the notes. So we got a coin here. Let's initialize it to heads because it has to be in one state or another state, right? Um, Now, again, that's the state of the system. The information we have the state about the system is a completely different matter. So it can be in heads, but we don't necessarily know it's in heads. That's kind of the crux of what we mean here by information, right? So we've got this heads coin, and in the notes, I believe we do a deterministic operation to take it to tails. Um, Now, when we say the deterministic operation, we don't mean this. That's not deterministic. That's probabilistic because we don't know the outcome with certainty of that operation. A deterministic operation would literally be take the coin, flip it over. Should probably have a coin for this demonstration. We actually do have a coin for. Bear with me here. Okay, yeah, so this is our quarter, and we have it in a state of heads, and then we literally take it with our finger and just flip it to a state of tails, put it down. Now it's in a state of tails. So that's just the state that it's in. Um, let's do the state space of this coin here. The state space of this coin is just one variable, which is f. We're gonna call it f for face, right? Um, but we're gonna represent the vector a little bit differently here. We're gonna represent the state space this way. Because again, state space is a vector, and you can put vectors in different bases, and we can rarely represent this any way we want. And how we're going to do it for the purposes of this and future computations in this lecture and in this course is we're going to say, because both of these specify the state of the system, right? Uniquely. If I give you the probability of heads and the probability of tails versus the face, these are both uniquely specifying the state of this coin. If I give you that the face is tails, or if I give you that the probability is 0 of heads and 1 of tails, these both tell you the same thing, which is that the coin looks like this. So that's our current state of the coin. Um, right. So let's do something a little bit more interesting to it. And, as alluded to, obviously, we're going to do the probabilistic version now. All right. So we got it in the state of tails because we just did the deterministic operation on it. And now we are actually going to flip it, the traditional sense, right? Okay. And I didn't look at it, so I don't know what state it's in. So I performed a flip operation on it, and now it's in some state where it's down there. I haven't looked at what the state's going to be. So how would we represent that? Well, it's a fair coin, we're assuming. So that means the probability is one half heads, one half tails. This is information. This is not a state. Okay, this is not a physical state. The coin is in a definite state of heads or tails right now, but the information I have about it is this. That's the information I have about the coin. Okay. Once I make the observation, happens to be in heads. This information state now in quantum mechanics, you're probably familiar with this terminology, collapse. It collapses to a state of what do we do? Probability heads, probability tails. That was the state space. Probably a probability heads, probability tails. That's our information vector here. So it collapses to what was it again? Heads. Okay. So now it collapses to this state instantaneously. And this is again information. Okay. New information was gained by making an observation. And you'll notice that each time here, every time the state or information about the state changes, there has to be some sort of computation behind it. First was the coin flip operation, and in this case, there was actually an observation operation. So an observation is kind of a type of computation under our definition, which is really interesting. So there's also the fact, this is really important. There's also the fact that your state is not necessarily the same as another person's, or the information about a state for one person is not the same as the information the other person has about the state, right? So I looked at that coin and I was able to tell that it was in a heads position. But you can't see the coin on your side right now. So you're just kind of looking, and for you, you're still in this state of information, right? Sorry, getting a little too Christmassy on you there. But for me, my state of information is this. So two people could have two different states of information about a system. Uh, we don't really complain about this in classical probability. It's everything's just kind of all right in that, because reality kind of still makes sense. In quantum mechanics, when this wave function kind of takes on a physical reality of its own, we're going to get into a little bit of counterintuitive trouble here, because this instantaneous collapse doesn't respect locality, right? So when I observe the coin, this instantly becomes that. It instantly does it. It doesn't have to obey speed of light or time space constraints or anything like that. That's what locality is. That's okay though in reality, because in classical probability and classical information, these things don't really have a physical reality. In quantum mechanics, they have a physical reality. So when something that's physically real and influences like physically real things we can observe, um, disobeys locality, we kind of have some issues. But don't worry, there's nice little loopholes, and nature's put guards in to protect locality in the end. But the fact of the matter, the crux here of what I'm trying to tell you is that you want to notice now this concept of a collapse, because this is what the quantum wave function collapse is. There's nothing quantum about a collapse. It has to do with classical probability theory, not quantum probability theory or quantum information or quantum mechanics or anything like that. The collapse occurs here in classical probability. It's simply how probabilities act, and it's how information in state acts in the classical sense as well. If there's no quantum physics, we would still have these collapses. The only ingredient that quantum physics adds is that the thing undergoing the collapse now has a physical reality to it. So I want to just, that's one of the main reasons I want to go over classical information right now. Yeah, I think that's enough for an intro to classical information for now. Okay, thanks for listening, guys.